Hello, we are the Physics of Railguns group. My name is Samuki. We have Sunny, Tanner, and Marcus in our group. We'll be covering what railguns are, some of their history, their real-world applications, advantages, disadvantages, and even a little problem focusing on the math and physics behind railguns and how they operate.
Railguns consist of two parallel metal rails, between which a projectile held in an armature is loaded, completing the circuit between them. A massive electrical current of the order of 1 million amperes is applied, creating an electromagnetic field, which in turn produces a force that accelerates the projectile along the rails. Railguns have numerous advantages over traditional explosive projectiles because of this acceleration force. It allows the explosive to reach a potential velocity of Mach 10 and a range of 220 miles, which is 10 times further than any other gun. Typically, a railgun projectile is not explosive. It relies on its enormous speed and acceleration to destroy the target. The kinetic energy of these projectiles can do as much damage as a Tomahawk missile. This also gives less risk of transportation and less risk of accidental fire on board a ship. The first instance of a projectile powered by an electromagnetic force to reach high velocities was back in World War I. A French inventor invented an electric cannon in 1918 based on the principles of linear motion. By World War II, a German scientist designed an electric anti-aircraft gun, but never used it. These early designs could send a projectile to a speed of Mach 5. The projectiles left the cannon muzzle with a force of 33 megajoules. These railguns were initially developed for land attack and anti-air weapons, but they were soon being used for other purposes as well. Because railguns are cost-effective, they started to replace many other weapon systems in both attack and defense. In modern times, most common places you can see railguns are along the coasts and on battleships. Railguns are very effective when it comes to water warfare because of their range and speed.
All right, now I will solve an example problem involving a railgun. So a railgun, as shown in this image here, is subjected to a magnetic field of 0.2 Tesla, a resistance of 2 ohms, and a current of 2 amps. The length of the projectile is 20 centimeters long. So we're trying to find what the speed of the projectile is. So to do this, we're going to need to first solve for voltage. And we're going to be doing this by using the equation voltage equals I times R. So we can use the given 2 amps and the given 2 ohms of resistance to solve that there is 4 volts in the system. Then we can use the equation EMF is equal to magnetic field times length times velocity, and we're going to be solving for velocity. So using this 4 volts for the EMF, we get 4 equals 0.2 Tesla times 0.2 meters, and then solve for velocity. So if you divide 4 by 0.2 squared, you will get the answer of 100 meters per second is equivalent to the velocity.
One real-world example that have someone use railguns today would be China. So according to Global Times, China has developed a railgun that have various sizes to a pistol to a rifle. The weapon is called a small synchronous induction coil gun, which is technically an electromagnetic railgun. Using electromagnetism, it could punch holes in various amount of material, such as wood and metal. These guns have a lot of potential because of how fast it can go and how quiet it is. It is still a prototype due to some issues with the range and the charge of the gun. This new technology could change the way conflicts are fought and are potentially better than a typical rifle. China is also developing a cannon-sized railgun to compete with the US Navy's railgun.
All right, here's going to be another real-world example of the US Navy railgun, and I'm going to show a video that kind of highlights just some of the firing of that.
Charges for 2 minutes and fires in less than 1 second. 1,800-page assessment stage. The system is shielded so as not to affect shipboard control system. The amount of electromagnetic energy released from this system is low, contained on the surface vessel. Clear at this time exactly which vessel will play host for the new weapon system. Back in 2015, Naval Sea Systems Command had announced plans to test the railgun aboard the Spearhead-class expeditionary fast transport USNS Trenton, substitute for the USNS Millinocket on the coast of Florida in 2016, but that test was subsequently delayed.
All right, so that was just a video highlighting some of the firing of that gun. So right now, the railgun works by using an extremely high electrical current, and then this generates magnetic fields that are able to accelerate projectiles up to speeds of Mach 6, which is currently more than twice as fast as existing projectiles. The railgun also has a range of more than 100 miles, and it uses a different tactic of attack compared to normal projectiles. So like Tanner mentioned earlier, instead of using projectiles that are highly explosive on targets, the railgun is fast enough to destroy targets with normal projectiles at hypersonic speed. The railgun has been waiting to join the naval fleet for a while now, and this is due to the lack of durability of the weapon. The kinetic power produced from firing the railgun is rough on the weapon's parts. A few shots can dislodge the conducting rails or even damage the barrel of the gun right now. The Navy thinks they can get to a point where the launcher core, which previously wore out after 10 shots, could fire more than 400 shots.
There are many advantages to using a railgun. One of the main advantages of a railgun is how low the cost would be for ammunition. Since there's no gunpowder or explosive material in it, the cost to make projectiles for railguns would greatly decrease. With cheaper ammunition, the railguns can accelerate particles 30,000 times the force of gravity and have a range up to 100 miles. This means that railguns could be alternative to artillery. On top of railguns being faster than regular bullets, it is virtually silent. There is no explosion happening in the chamber, so there would be no sound because the bullet is being accelerated by electromagnetism. But with so many benefits, there is also a downside to railguns.
Some of the largest disadvantages about railguns is how they require these large amounts of electrical energy to fire the projectile at the energy you need for it to be as effective as the Navy claims. Um, a big problem with this is a lot of the ships that the Navy has doesn't actually create or conduct as much electricity as the railguns need. So the only current Navy ships that can actually support a railgun as a solution are the aircraft carriers, and there's very few of them. Another problem that Marcus went over earlier was the large amounts of friction and wear on the rails as the projectile accelerates through it. Makes it require very frequent repairs and rail replacements, which currently is a very large problem. And another disadvantage that I guess you could see as an advantage one day is that it's very new and it doesn't have all of these problems worked out yet. So things are being solved as it goes. So maybe what we say today about railguns won't be the same in a year or 2 years or in a decade. And I think these are the largest disadvantages revolving around railguns. And I guess this wraps up our presentation about railguns in general. We went over the advantages, the disadvantages. We went over how the Navy is currently using railguns, how people internationally are using railguns, sort of the history of it, and we also went over a problem about it. And personally, I think railguns are super interesting because they kind of serve as this intersection of electricity and this technology we knew existed, and basically using things we knew before in new, meaningful ways as technology develops.
And here are our references that we used to compile this presentation.